Okay. Okay. So yes, this is the eighth class on this electromagnetic theory. And if you remember, till now we have discussed about electrostatics, magnetostatics, Maxwell's equations, and all that. Today we'll slightly change gear, and what we'll be talking about is actually transmission lines. So one of the major applications of electromagnetic theory is in circuits and networks. Okay. And in general, when we normally talk about circuits, we do not take into account the effects of the transmission lines. So we say that there is a resistor, there is a there can be, inductors, capacitors, and all that. But the wires connecting them, we don't take into account this connecting leads and the impact of the effect of this connecting leads, because the connecting wires or leads are nothing but some conductors which can have a net resistance. There can be some inductance because there's a current flowing through it. There can be capacitance when you have two wires close to each other. So all these effects can come in under different conditions, which in normal cases we don't really care about. But what we will discuss today is that under what conditions these effects become really important and where we can neglect them. Okay. Yeah. So basically, the normal circuits where we don't take into account the effect of this connecting leads or the effect of the wires is what is called a lumped circuit. Okay. So basically, in a lumped circuit, if you have some input current, so consider it to be some lumped element, some uh, connecting wires or something. So here, if you have some input current and it goes through this element, and then you have this I2 current, so I1 and I2. And as you can see, it has no effect. So both are same. So there is no effect of the connecting element there. But now imagine the situation where you have this lumped element where the current entering and leaving the lumped element is the same, but you have connection leads around it, right? So you start from a point, you have a connection lead, you have some lumped element, and then you have another connection lead which leads it to point B. Now, these connection leads can have certain effects. So what can happen is that, so if you start with a current like this, at some later point, the current can have some phase difference. It can have some distortion. It can have some decay. Okay. And there can be some delays coming in. So the connection leads can cause delays depending on the lengths of this connection leads. So this is called a distributed circuit. Okay. So in this kind of condition, so first we want to see what is the regime where we have distributed circuit and what are the conditions where we can consider our circuit to be a lumped circuit. Okay. So there could be different regimes. So first is the lumped circuit regime where basically the dimensions of your components are much, much smaller than the wavelength of your signal that is transmitting through them. Okay. So there what happens is because the wavelength is quite large, we can ignore the effect that comes in because of the dimensions of your connection leads. Okay. So we consider that here the voltages are not changing as it passes through the wires. Okay. And it's basically the electrostatic limit because here what we are considering is it fits with this condition that the surface of the conductors are considered to be equipotential surface. And that's the reason why we can assume or we can consider that there's no work done in moving or in because of as the current flows, there's no work done as the charge moves from one point to another over the surface of your conductor, no work is done. Okay. So it's the electrostatic limit. And here because the wavelength is much, much larger than the dimension, so one can ignore the wave nature and you would later see that Kirchhoff's law can be applied in this regime. Okay. While there can be another regime, which is where the dimensions are much greater than the wavelength of light. So under those conditions, the waves become like rays. Okay. So that's the ray optics regime. But what we will be focusing today is this regime, which is the transmission line regime or the distributed circuit regime, where the dimensions of this connection leads are comparable to the wavelength of the signal, that is being transmitted. Okay. So when can this happen? So in real life, if you talk about cases where the frequency of your signals are in gigahertz range, that would mean the wavelengths are typically around some tens of centimeters. So now if you have wires comparable to this length, then that would be the distributed circuit regime or transmission line regime, where the connection leads will play a role. Okay. And here, because they're comparable, we cannot ignore the wave nature. And this things is what happens when when you deal with microwave circuits or optical fibers. Now, if you have some sinusoidal signal with some frequency, we know that for that frequency, we can find the typical wavelength that our signal has. Okay. And accordingly, we can decide whether we are in the transmission line regime or we are in the lumped circuit regime, right? But now if you have some kind of a digital signal like this, so in digital signals, what is expected is something like this, right? Like a square wave. But in nature, we always have something like this. So there is a rise time, a finite rise time, and a finite fall time. So if you consider such kind of a switching waveform, a typical saturated ramp kind of signal, and if you try to find the power spectral density for this, you will get something like this. So there would be some power for different, so there'll be a distribution of power over different frequencies. So now if you choose the frequency which, like, till which there is the maximum power that is there, so that corresponds to some f max value, right? So you can choose based on your signal. So this f max will again then correspond to the shortest wavelength of your signal. So the major part of your signal lies in this range, which corresponds to where the shortest wavelength is given by this. So now, if your length of your connecting wires, if they are comparable to this uh, lambda short value, then we are in the distributed regime, and otherwise we are in the lump circuit regime. But it's important to note that how much is comparable, right? So we generally take it as 0.1 times. So if your lambda short is around 1 centimeter, then if your L is more than 0.1 centimeter, okay, in that case, so so if it is 1 second, what have I written? Yeah, I have written it correct. Yes. So basically, now if your lambda short is 1 centimeter, that means now if your dimensions of your wires, if it is much more, okay, if it is much more or comparable to 0.1 centimeter, then we'll be in the distributed circuit regime. Or if it is much smaller, so if the dimensions are smaller than 0.1 centimeter, in that case, it will be considered as a lumped circuit regime. Okay. So now what happens when we are in the distributed circuit regime? So we saw that the transmitted line has some effect, right? Now, how does this effect come in? So it turns out that one can consider this effect of the transmission line in terms of this following parameters. So you can consider that your wire, the connecting wire, has this following effects in terms of some resistance, some inductor, some conductance. Because the resistance is in parallel, so it's considered as a conductor, and some capacitance, right? Now, how is it originating, right? So why do we have a conductance? Why do we have a resistance? Why an inductor? So basically, consider that some signal, okay? So if you have something like, so consider you have some source, just ignore this problem. So some source, okay? And then you have some connecting wires. That's how your circuit goes, right? Now, what are these wires? These wires are nothing but some conductors, right? Now here, what you can have is some positive terminal, some negative terminal, right? Now in between this positive and the negative terminals or the connecting wires, it you can have some dielectric. So consider if you have a coaxial cable. So there you have a dielectric present between your positive and the negative terminals, right? So now if there is some leakage there, so if the dielectric is not completely perfect, in that case, there'll be some leakage between the positive and the negative, and that will give rise to this term here, the conductance. Okay. So conductance, because it's connected in parallel, resistance connected in parallel is equal to conductance, right? So this leakage is taken care of by this term here. Okay, so the G models the imperfectness of the dielectric. So in nature, if you have normal connecting wires in free space, then this will be free space. That the dielectric will be air in that case. Okay. Now this connecting wire. So we are trying to see the effect of this wire and this wire, right? So these wires obviously will have some net resistance. They cannot be of zero resistance, right? So there'll be a resistive load that these will correspond to, which will be in series along the wire, right? And again, because you have a current flowing through it, so there can be a net resultant inductance that can be developed. So that give rise to L. Okay. And now because you have two such wires, right? So you have this wire and this wire. So there are charges, free charges in this wire and then in this wire. So in between there's this space. So that means there can be a net capacitance that can generate in between these two surfaces, right? So C indicates the region between the two wires which can make up a capacitor. So that means the effects of the transmission line can be considered in terms of this four parameters, right? L, R, C, and G. And if you can note, it's important that this parameters, why are they called distributed, is because you can see it's written in terms of, uh, per unit length, right? You have inductance per unit length, R per unit length, G per unit length, C per unit length. And these values will also depend on the position where you are in your circuit, right? So if you have a circuit, the value here might differ from what you have here. The impedances that they see will be different. So that means they are these parameters are distributed around in the circuit, and that's why they are called distributed parameters. Okay. Now, what you can in general do is that, so if you have such a circuit like this, so you can break this circuit into number of segments such that each of these segments are small enough that you can consider them as a lumped circuit. Okay. And in each of these elements, you have this effects of L, R, C, and G. And then you have similar such segments in parallel. Okay. So how do you choose your delta Z, or how do you choose that segment? Depends on what is the shortest wavelength that is propagating through your signal. So your delta Z should be much smaller than your lambda short. Okay. And in each of these segments, because each of these segments are in the lumped circuit regime, we can use our Kirchhoff's laws. Okay. And we'll see how we use them. Okay. So now, before we see how we use them, we can see that the Kirchhoff's laws can also be derived from the Maxwell's relations. So we know this is how the Maxwell's relations look like. And now, if you have no time dependent, if you have no time dependence, that means your del B del T term will go away. Your This will always be zero. And again, here you will not have the del E del T term, right? Now, because there is no time dependence, that means del rho del T is zero, which gives us that divergence of J is equal to zero. And now if you think closely, this is nothing but your Kirchhoff's current law. What does the current law say? It says that at a node, the amount of current that is entering is equal to the amount of current that is leaving. So this is essentially the same, which says that there should be no charge accumulation at the nodes, right? Because del rho del T is zero. So that's how you can start from Maxwell's relation and go to the Kirchhoff's current law. Again, because there is no time dependence, so del B del T is zero. That means curl of E is zero. So from here, you can write it in terms of a line integral. And then this gives you the Kirchhoff's voltage law, which says that in a loop, in a closed loop, your sum of all the voltage drops should effectively turn out to be zero, right? So this is your Kirchhoff's voltage law. And we'll see how we use this laws in those individual segments. Okay. Okay. So now when we apply the Kirchhoff's voltage law in the unit cell, which comprises this R, L, G, and C. So we have this is the just normal KVL. Okay. So you start with some potential drop here. Okay. And there is a different potential here. Right. So you can say that this is the potential at this end. There will be a drop at the resistance, which is given as R delta Z minus R delta Z. And then there'll be another drop here, which is given as minus L del I del T into delta Z. Okay. And so basically you are taking this loop, right? You're taking this loop. So that means, and then you write it as minus V Z plus delta Z. So that gives you an entire loop. Now for this loop, you apply the KVL and this is the relation that you get. Okay. Now this happens, so you can take the limit where delta Z tends to 0 and then you can write it in terms of the derivatives. Okay. Similarly, you can apply KCL at this node N. Okay. So the amount of current that is coming in is given as I, Z and T. Okay. And there'll be current living through the conductance, the capacitor, and there is this current I Z plus delta Z, which is living in this direction, right? So if you write all those terms, you would get this from the KCL. So now we'll see how one can use this, these two relations to see how the potentials vary as we move from one end of your transmission line to another. Okay, so as we move from one end to another, we would see that all these effects of your distributed parameters will play a role in affecting your voltage and the current that you see. Okay. Yeah. So now what one can do is one can take first the condition where R and G is 0, which we consider as the lossless case. Okay. So in this condition, if we try to solve these two relations, so here R goes to 0, G goes to 0. Okay. And then we can do a double derivative of these terms, and that would give us some expression like this, right? So now this is nothing but a wave equation, right? So here LC can correspond, so 1 by root over LC can correspond to the wave velocity that you can get. So basically now what you're talking about is that your voltage that is traveling through your transmission line has the form of a wave. Okay. And here, when you solve it, so you would get a forward wave and a backward wave with the effective wave velocity given by this term here. So it depends on L and C from your distributed parameters. Okay. And we we know that V is equal to IR, right? So using that relation, you can find the characteristic impedance of your unit cell, and that is given as V plus by I plus. Okay. So in terms of the parameters, you can write it as root over L by C. Now, what we will next do is we'll consider the sinusoidal response of transmission line. So that means, so suppose if you have some time varying voltage at one end, okay, and you have the transmission line, and now you want to see what do you get at different instances in the transmission line, okay, taking into consideration the effects of your connecting wires. So here we will use the phasor representation. So we know that if you have some signal like this, so V naught cos omega t minus kz, you can write it as real part of V naught e to the power j omega t minus kz, right? So it's the phasor representation. And then you can try to differentiate write it separately, right? The spatial and the temporal parts separately. But once you have this form, so now you can try to use your expressions that we had derived, right? This expression and this expression. Okay. So if you use that, if you use the first expression, you would get something like this. So here, when you have del V del Z, okay, and then you have minus IR and L di dt. So here del T would correspond to J into omega. Why? Because you have this time dependence here. Okay. And integration means 1 by j omega. So you can use these relations to get to this expression. Similarly, for the KCL equation, you can get an equation like this. So now if you try to look at both of these equations together, and so if you do a double derivative of this equation, okay, so d square v dz square, and then you will have a del I del z here where you can replace by this expression. So you would get something like this. So what you are getting now is a equation which is del square V del Z square is equal to minus gamma square into Vz, where gamma is given by this expression here. Okay. So that means now you can write V, which is your potential or voltage, in terms of a forward and a backward moving wave with this terms here, right? This gamma is your propagation term. And as you can see, it's a complex quantity. Okay, so here you have it as alpha plus j beta. Now this alpha here term, it takes into account the attenuation that can happen. So when you start with some potential here, voltage here, and as it is transmitting through the wire, there can be some attenuation in the voltage, and that is taken care of by alpha, while beta takes care of the phase that can come in. Okay. So now when you have lossless case, that means in lossless case, your R and G would go to zero. Okay. So there, what would happen is alpha would go to zero. So you can check it out. So now if one considers only the forward moving wave, that means you only have this term here. Okay. So V naught plus e to the power minus gamma z. Now with this, if you have only forward moving wave, you can use this expression that we just derived to see that now you can write a ratio of your potential to current at a particular z. Okay. And you would see that this would depend on your distribution parameters by this relation. So this is a very important relation because this, so this gives you some, the characteristic impedance of your transmission line. So your transmission line now corresponds to some net resistance that it applies to your voltage or the current that is propagating through it. And that is signified by the characteristic impedance. Okay. So this relation is very important. And here, as you can see, because it's a complex quantity, that means V and I are not in phase. Okay, because you have the complex term, you would have a net phase difference between the two. Okay. So now this is your relation for the characteristic impedance of your transmission line. So let us look at the different cases that can come in. Okay. And each of these cases would give you new formulas, which can be directly useful in solving different questions. But I would ask you to basically understand how you get there and remember this because all this can be derived from this itself. Okay. So now in the lossless case, where R and G is zero, you can now see you get back the same expression, right? The one that we had initially seen in two slides, like two slides before. Okay. So it's a real quantity. Okay. So it's like normal resistance. So here in this case, they will be in phase. Okay. Because your R and G, both are zero. Okay. Now what happens when your operating frequency is large? Okay. So in that case, your omega L will be much greater than R and omega C will be much greater than G. So there you see that now your propagation uh, factor, the factor that we had here, the propagation term, that is reduced to j omega root over LC. Okay. And Z naught again matches with what you get in the lossless case. So that means high frequency case is similar to the lossless case. Okay. Now, another thing could be is that there could be distortions, right? So one is attenuation. So your voltage gets reduced. But now the form of your signal can also get distorted as it moves from one end of your transmission line to another. Okay. If that does not happen, then it is a distortion-less line. And when does that happen? When the series time constant is equal to the parallel time constant. So what we mean by that is the series time constant is given by L and R, while the parallel time constant is given by C and G. Okay. So when these two terms are equal, then the distortions do not happen. Okay. So when L by R is equal to C by G, that is a distortion-less line. Okay. And you can see that, from here using this relation, you can try to write alpha, which is your attenuations. There can be attenuation. Okay. Attenuation is different from distortion. So this is attenuation, and this is how the expressions look like for a distortion-less line. Okay. Now, because it's a wave now, so that means the wave will have some velocity, right? So if you have some voltage in this form, V naught cos omega t minus beta z, then the phase velocity for this wave would correspond to some omega by beta, right? So now for the lossless case, we know that beta would be given by this expression, right here. So because your alpha is zero, so gamma is equal to beta, which is given as omega into root over LC. So if you use this expression here, you see that this is the same expression that we had initially got, right? This is the expression that we had got from solving the wave equation, and the same thing comes up here. Okay. Now, if there is an attenuation, so now if it is not lossless, so if you have a net alpha is non-zero, so that means your voltage amplitude can now decrease as it transmits from one side of the transmission line to another. Okay, and it has this kind of a exponentially decaying uh, function, which is given as v naught plus a to the power minus alpha z. And you can write it in terms of dB by this relation. So basically, if in questions, if it is said that suppose at this point, you at z equal to some z naught, you know the potential or the voltage, and it said that at z equal to z naught plus delta z, this is your voltage. Okay. So now if it is asked what is your alpha, so from there you can use this relation to find alpha, but that alpha will be in the natural units. Okay. So you can change from natural units to dB by using this relation. This is just a a measure, a way of writing the same thing. So if you want to write it in terms of dB, then this is the relation that it has to hold. This is in natural units, this is in dB. Okay. And you can also write the reverse relation. So in general, when you talk about, when in questions, if you have voltages at different locations, the alpha that you would get will be in the natural terms. Okay. And then if you want to find it in dB, you have to use this relation, or otherwise use the reverse. So there could be similar kinds of questions which directly uses this formula. Okay. Okay, so now based on what we just discussed, we try to solve some questions. Okay, so here it's a TEM mode transmission line, and here it's said that R, L, G, and C is given. So which of the following is true? So this is pretty straightforward. We try to use the conditions that we just learned. Okay, so here for a lossless line, we know that R and G should be equal to 0, right? So that is not the case because R and G is non-zero. So that means it's a lossy line, it's not lossless. Now for distortionless, we know that it has to satisfy this relation, and you can see that this holds. So in this kind of questions, be careful about the units that are specified. Okay, this microsec and Siemens, and then you have this nanohenry. So this be careful about that. So now what you get is that from this you can see that it's a distortionless line. So there could be pretty standard, straightforward questions like this from what we just discussed. Okay. Now, another question here is a lossy transmission line has resistance per unit length, which is given. It's distortionless. That means it satisfies the relation which we just discussed, right? R by L equal to G by C. And it has a characteristic impedance, which is given as 50. So you know the Z naught characteristic impedance of your line. Now the question is, what is alpha? What is the attenuation constant? So in this question, how do we do it? So what are the informations provided? We know R, we know it's distortionless, and we also know the characteristic impedance, which is given as Z naught, right? So here, what we will try to use is this relation, and we'll see how we can get to the expression of alpha. So it's very important because this tells you how one uses the formulas to get new relations, right? So here you see that this is what we discussed. This is the distortionless condition. Okay. And this is the expression for your impedance, characteristic impedance. So now because this holds, you can write Z naught in terms of R and G now. So if you use this relation, you know Z naught from your question. Okay. You know R. So you can use it to find G. But what we want to find is alpha. Now, how do we get to this expression? So basically, now we want to find the relation which involves alpha, R, and G, right? So how do we use that? So we have to go back to this expression here, right? So here alpha is given by R into root over C by L is equal to is equal to G into root over L by C, right? So now if you write alpha square, and what would be alpha square? So that in one side you have alpha square, other side you try to multiply this with this, right? So alpha square will be equal to this into this. You can do that. So if you do that, these terms will cancel each other. So what you would get is alpha square is equal to Rg. So now you get a new relation which relates alpha with R and G, and this is the relation. So once you find G, you already know R, so you can use it to find alpha. So it's important how we have used the previous relations to find a new relation, right? So here you first know R and Z naught. You use this relation to find G, and then you use this relation to find alpha. Okay, and important to note, you're getting it in natural units. Okay. So now till now what we just discussed was, okay, 1 second. I'm sure it won't go. Okay, so I don't know this some network issues. Okay, so now what I meant is that till now what we discussed was two transmission lines, right? But we just did not discuss what we have at the other end. So in nature, normally in physical circuits, you would have some way of terminating these lines, right? So if you have some load at the termination, what happens, right? How do we work out those questions? So here, that means you have some source, you have some transmission lines, and then you have a load at the other end. Okay. So in this cases, what you can consider is that you can consider this as your z equal to 0 line. Okay. And along this, you will have your z, right? So that means,
What is the answer for previous question, ma'am? 0.01. Is it alpha equal to 0.01? Point not one. Okay.
yeah.
Is it we need to write it in natural or logarithmic exponential term? If suppose
So
if they ask it in dB means only we have to do it in
yeah,
logarithmic.
if it is in dB, yeah, then you can use this relation. You can directly use this relation to find it in dB per meter. Okay.
Okay, thank you.
Yeah. I think there could be some very straightforward questions which make use of this kind of conversions. Yeah. Okay. So now in general, if you have some kind of a termination at the other end, so that means you can take this as your z equal to 0 line. Okay. And the transmission is taken along this direction. So that means you have your load at z equal to 0, and you have, if your transmission length line has a length of L, that means your source is at z equal to minus L. Okay. And we know now that your voltage or the drop at the source is not equal to what you have at the load. Okay. But there should be a way of some boundary condition which tries to balance this. Okay, so balance in the meaning that your voltage or your current should not, uh, your voltage or the current should not suddenly, discontinuously vary. Okay, so there should be a continuity which relates what is the voltage drop at this end. Okay, there is a transmission, so the voltage changes, and once it reaches the load, it has some voltage which also will have a dependence on the load impedance, right? So how do we do this continuity? So there has to be some boundary condition that needs to be satisfied. Okay. So in general, we know that this is how your voltage looks like on a transmission line. And similarly, if you know the characteristic impedance, you can write the current by using this relation. Okay. So now let us see how the boundary condition looks like at the load. So at the load, that is at z equal to 0, your whatever be the expression, so your V0 by I0 should be equal to ZL, right? Because that is your load impedance. Okay. So that means if you put Z equal to 0 and try to find the ratio, that means this would be the relation, right? Basically, what you are doing is you are putting Z equal to 0 here, Z equal to 0 here, trying to find the ratio of the two and equating it to ZL. Okay. So this gives you a relation which relates ZL, that is the load impedance, with the characteristic impedance of your transmission line. Okay. And importantly, this term comes in, which is a ratio of your, forward moving wave and the backward moving wave, right? So this is nothing but the reflection coefficient. So this tells you that now the load, the load impedance does have an effect, okay, on your, does have a relation that relates it with the characteristic impedance of your circuit. Okay. And they are related by the reflection coefficient. So the reflection coefficients can also be found. This is just a way of doing ratio and proportions, and you can write the reflection coefficients in terms of your load and characteristic impedance. Okay. Now this is at the load. Now what happens at the source? So at the source, you have to put Z equal to minus L, considering that the length of your transmission line is L. Okay. So again, you use the same relations, and this would give you the relation which relates your, now this is your incident impedance, right? So Z incident with Z naught. So it's important to note that now Z incidence, which is your, the incidence at the source, that is related to the characteristic uh, impedance of your transmission line, that is related to the length of the transmission line, and that is also dependent on the load impedance. Okay, so the load impedance and the length does affect the impedance that is seen at the source, that is Z in. Okay, and this is how they are related. So we can consider different cases based on that. Our, this is the main expression. Now, based on different conditions, we can simplify it further. So if you have a lossless case, that means your alpha is 0. So you can write gamma as J beta. Okay, and this is how it will look like. And then under this condition, you can have when ZL is equal to Z naught, that means the load impedance is equal to the characteristic impedance of your transmission line. Then Z in is equal to Z naught. That means the incident impedance also matches with the characteristic impedance of your line. When load is 0, that means it's a short circuit. So then your incident impedance looks like this. Okay. Again, if you have load is infinity, which is an open circuit, then this is how it looks like. Okay. And because it has this beta L term, that means based on the length of your transmission line, you can get different values. Okay. So when beta L tends to 0, your Zin is equal to ZL. Okay. When beta L is equal to pi by 2, your Zin is given as Z naught square by ZL. And when beta L is equal to pi, again Zin is equal to ZL. This is very important. Particularly, this relation is also very important, which tells us that now, based on the length of your transmission line, the impedance that is seen at the source varies. Okay. And if, in particular, if the length is such that, so if the length is, this relation is nothing but writing length as if the length is equal to lambda by 4, right? If lambda is the wavelength that is being transmitted, if L is equal to lambda by 4, then your Z incident is related to your Z naught, that is the characteristic impedance, and the load impedance by this relation. This is a very important relation. Okay. Okay. So now this question says that the input impedance of short-circuited lossless transmission line quarter wavelength is. So what are the information? First is we have to find the input impedance. That means we have to find Z in. Okay. Short circuited, that means your ZL is 0, right? And it's a quarter wavelength transmission line. That means this condition, this condition has to hold, right? Quarter wavelength, because that means L is equal to lambda by 4. So this is the relation that relates your Z in with Z naught and ZL. And for your question, ZL is 0, right? So now you know what your Z in should be. If ZL is 0, your Z in should be infinity, right? So that is what we can find. Okay, so Z in is equal to Z naught square by ZL. ZL is 0, so Z in is infinity. So that means for this case, your input impedance at the source or at the incidence will be infinite.
Ma'am,
Yeah.
here that wavelength is a quarter wavelength, but in the equations you mentioned that the wavelength is lambda by 2, half wavelength. How it is exactly match, ma'am?
No, this is pi by 2,
Beta
right?
pi by 2, it's a half wavelength, no? Lambda.
No. See, 2 pi it corresponds to lambda, right? A 2
Okay,
pi
okay, 2.
phase would be corresponding to lambda.
Okay, okay.
So, yeah. Okay.
Okay, ma'am.
Yeah. Okay. Now, I think we have a similar question in our, like I saw a similar question in the last year's assignment. Similar questions might also be present this year. So, here what it is saying is that, you have different transmission lines, okay, all one after the other. And we have the value, this value is provided. We have to find Z01. That means we need to find the characteristic impedance for this part of your transmission line. Okay, your starting transmission, this is the load impedance, which is given 150 ohm it will be. So this is your load impedance. Each of these transmission lines are of quarter wavelength length. Okay, your Z naught at the incidence is given. So this is the characteristic impedance of this part of your transmission line. You know the characteristic impedance of this part, which is given as 30 ohm. What you have to find is the characteristic impedance for this part of your transmission line. So how do we do it? Okay, so the first thing that one has to start with is that let us start with this part. Okay, so here we know it's a lambda by 4 quarter wavelength transmission line. We know the characteristic impedance of the transmission line. We know the load. Sorry, I'll just erase these things. Yeah, so we know the load, we know the characteristic impedance, we know the length. So using this, can we try to find what is the incident uh, impedance at this end? So can we guys try to solve it together? So we know Z naught, we know ZL, right? And it's a quarter wavelength transmission line, right? So we can then use this relation. We know Z naught, we know ZL, we have to find Z in, right? So what would be Z in for this part? Can you tell me? I'll open the chat.
ZL.
Yeah.
Z naught square upon ZL. Z naught is for input impedance of second lambda by 4.
Yeah, right. So what is this value?
It's
What will be this value? 30 into 30 by 150, right? Tell me what the value will be. Like I want you guys to solve it. That's the reason.
6.
So, okay. So this is the value that you have here, right? So that is now the load for this part of your transmission line, right? So for this part, now you know the load. You have to find the characteristic impedance and you know the length. So for this, that means if we again use this relation, we now know the load. We have to find Z naught. So we need to find Z in, right? So for this part of the transmission line, we need to find what your Z in should be. What is given is the characteristic impedance for this transmission line. We need to find Z in here, right? Here we have to use this relation that there is no reflected wave present beyond A, right? So if there is no reflected wave, that means the impedance must match, right? When we have a reflected wave, that comes in because of a impedance mismatch, right? So that means the impedance that you have along the transmission line, if the impedance is the same as what you have here, then there is no reason for the wave to get reflected, right? So that means this is already telling you that your Z incidence here is equal to 100 ohm. So this is the relation condition that tells you that Z in for this part will be 100 ohm. So now you know Z in, you know your ZL, you have to find Z naught, right? So can you do that? So what will be Z naught 1 then?
Is it 30 month?
Yes.
30.
Okay, it's little hazy. I can't understand. But basically, we are trying to do something like this, right? So, did you get a similar result? Yeah.
Yeah,
Okay,
ma'am.
so this is how we can try to solve this kind of questions. Okay. Okay, now this was another question from the last year's assignment, which said that now again you have a lossless transmission line. Okay. And that means lossless meaning your R and G is 0. Okay.
Ma'am, pardon. Here we get 24.49. So we have to mention 24.49 in the answer, or we have to mention it approx 25.
It depends on your options, whatever options are present. Basically it's, if you have to round off, you can round off, like, doesn't matter, right? So
If
if
option is
whatever
not
is the
given,
closest option, whatever is
if
the closest,
if
yeah,
option is not given, then we have to mention 24.5. Is okay?
yeah, you can write it as 24.449 also, whatever you have got, you can also write that. It's basically just rounding off, right? So
Okay.
anything will work.
Ma'am,
Okay.
one small doubt. Here,
Yes.
150 into 6, 900, square root of 900 only, no. But how it's a 600?
Yeah.
Yeah, ma'am. Ma'am, you
150
have
into
Yeah, tell me.
150 into 6. 150 into 6, 900 only, no.
Why will we do 150 into 6?
Is it OL square equal to 150 into 6?
One
Is it
minute.
is 150? So
ma'am,
150 equal to,
Please, one person at a time. I'm just getting confused. Yes, tell me.
so here, so comma 150 equal to Z01 square divided by ZL. So ZL is
This
6.
term, this one,
150 into
right?
6.
This one you are saying.
Yes.
This.
Hmm.
So here you don't, your
No,
ZL
ma'am,
is given,
that
right?
multiplication is here and no. 150 into 6.
150 into 6.
600. How it will become 600? I'm saying it is 900.
1 minute. So first we are trying to look at this part of our circuit. Okay. So here, this is
Ma'am,
ZL.
I'm setting it is typo error or
So I'm not actually
mathematical
getting
multiplication
the.
error.
Just 1 second. Actually, I'm not getting where the problem is. So here, for this question,
Ma'am,
like this part.
here, so, comma, 150 equal to, in that end, 24.5, above that step.
Okay, yeah,
Z
yes, here.
not 1
Okay.
square equal to 150 into 6 equal to square root of 900, correct?
Why will it be 150? It is 100, right? Your Z in is 100, right? Here we are. So 150 is here.
But you mention it is like a 50.
No, don't get confused. First, we will use ZL as 150. Okay. Your Z naught is 30. So that means we need to find what is the impedance, input impedance
Yes,
for
ma'am,
this part
correct.
of the section.
Here, that is a typo
Please
error,
let me
correct?
come. 1 second. Please let me complete. If you still have doubt, you can ask me. Okay. So first is
Okay.
you use 150 and 30 to find the input impedance in this part of your section. Okay. So that is 6. That acts as your load for the next part. For the next part, your this condition that there is no reflected wave tells you that the Z incidence here is 100. So now your Z incidence is 100. Okay, so that means this is 100. And here you have ZL is equal to 6. You have to find Z01. Okay, so it is 600. And root over of 600 will give you Z01. Is it clear now?
Okay, ma'am. Okay.
Yeah, it's not 150, right? It's 100. Okay.
I'm saying that whether you made a typo error 150, you are saying
No, this is
100.
not 150. This is 100. This is not typo. I think I don't know what you're saying. It's 100. This is 100. This is
100.
100.
Okay.
Yeah.
Okay.
Okay. So now this is another question, which again says that it's a lossless transmission line. So that means your, 1 second, guys, just give me 1 second. There's some, 1 minute. Very sorry, guys. Just there was one call from a long time. Yeah. Okay. So this was another question which can just go to the slideshow. Yeah. So here in this question again, it said that it's a lossless transmission line with the length given as lambda by 4 and Vs is given. So at the source, we know the voltage. Okay. And uh, this is the voltage of the potential at the source. There is an additional impedance here. Okay. And this is Z in, that is the incident impedance at the start of the transmission line, which is not given. This is what we have to find. Okay. And ZL is given. Okay. And yeah, that's it. So now we have to first find Z in. So this is very straightforward, right? So we know that the length is lambda by 4. We know ZL, we know Z naught. So we can directly use this relation, right? Sorry, where is the relation gone? We can directly use this relation, right? So if you use this relation, we know Z naught and ZL, we can find Z in. So that part of the question is pretty straightforward. So you would get, you can try to solve it. Now, next part is interesting because it says find V in V. So we know Vs. We have to find V in. So here we will use our normal understanding of circuits. Okay. So if you solve here, so as far as I remember, I had solved it before. It was 100 at the, like Zn came out to be 100. Okay. So now here, that means you have some resistance here, and there is some resistance here. And this is your voltage. That means now it is like a voltage divider, right? Your voltage, there'll be some drop here and some drop here. And if they're equal, that means there'll be equal drop. So that means at V in, there's no reason for it to have any additional extra phase. So the phase should remain the same, right? So whatever is in the phase should remain the same, but your amplitude should now get divided between these two resistors. So if you have 100 ohm here and 100 ohm here, that means now your 10 should become 5. So the V in should be like 5 e to the power j 30, right? So that's how, if there was some other resistance which was not equal to 100, then you have to use our normal understanding of how voltages get divided, right? The normal understanding of voltage divider circuits that would tell you what is the net voltage that one can get here. Okay. Now this is one part. Now the another part was to find VL in terms of volts. Okay. So how do we find VL? So we know Vs, we know Vn, we have to find VL. So here again, we will use our known relations. Okay. So we know Vin, and Vin is nothing but V at Z equal to minus L, right? So that is given. That is what we found from our last question. We have to find VL, which is equal to V at Z equal to 0. This is the general expression of potential as a function of Z. Okay. So if you take V naught plus common, then you can write it as V naught plus into TL here. That TL is your reflection coefficient. Okay.
Ma'am, excuse me, ma'am.
Yes.
Kindly provide the answers.
Yes.
Kindly provide the answers.
So the problem is that this kind of similar questions come in your assignments, right? So we are not actually, like, what was told to us is to solve similar questions, but not discuss directly the answers, so that you get an idea, but you solve it yourself. Okay. So I would ask you that based on whatever you're discussing, so I'm pretty less just going to the extent of solving. So just do the steps as I'm telling you. You will get the answers, because that's what was told to us when we started with the course. Okay. So if you have any doubt in the process, you can ask me or follow the steps, you would get the answers. Okay. So here you have, so this is the potential at different Z values. Okay. So now for a lossless transmission, because this is lossless, that means alpha is 0. So you can write gamma as J into beta, right? So that means you can replace gamma as J beta. and Z as minus L and use this relation, right? You know what is V at Z equal to minus L. So put Z equal to minus L, okay? And this is what you would get. Now, this is equal to what you know. This is already known to you, right? So from here, you can try to find what is the expression for V naught plus, okay? So here, V naught plus is given as V of minus L, which is known by e to the power j beta L plus T into e to the power minus j beta L. So here, T is your transmission reflection coefficient. You have to find it. Okay, this is not known to us yet. So you have to find T, and we know what is beta L. Why? Because we know it's a lambda by 4 line, right? So your beta L should be equal to pi by 2. So you can replace it by 90. So all the terms here is known except T. How do we find T? So we will again use this relation. So if we go at the definition that we discussed, we know this is how the coefficient, reflection coefficient is related to the load and the characteristic impedance. So your Z0 and ZL is already given to you, right? So you can use it to find TL. Once you find TL, that means in this expression, you know all of it, right? So from here, you can find V0 plus. Now, what is the question asking? We have to find VL, right? VL is nothing but V at Z equal to 0. So here, if you put Z equal to 0, you would get VL as V naught plus e to the power 0 plus TL into e to the power 0. E to the power 0 is 1. So that means VL is equal to V naught plus into 1 plus TL. So now you know TL from here. You know what is V naught plus by using this relation. So that's how you can try to find what is VL, right? Is it clear to you? Is the process clear to you?
It's clear, ma'am. It's clear.
Yeah. Okay, thank you. Yeah. So now another thing is, so because you have a reflected, a forward moving wave and a backward moving wave, so that means there can be standing waves that can generate, okay? So for lossless lines, so where your, for lossless meaning your alpha is 0. So now your gamma is only replaced by beta, right? So that means this is how you can write it. This is your potential at different Z values. Again, you can write your V naught minus in terms of V naught plus by using your reflection coefficient. And in general, your reflection coefficient can be a complex quantity. So you can write it as some modulus into j to e to the power j phi. So your phi is your argument and this is the modulus. Okay. So that means in general, you would have some additional phase that would come in. Okay. So this is a general case. Now different cases can arise based on what your ZL and Z0 are, because that would determine your reflection coefficient. Okay. So if ZL is equal to N into Z0, that is N times Z0, then this is how your reflection coefficient look like. Okay. So here, if you put N equal to 2, that is when ZL is equal to Z0, your reflection coefficient turns out to be 0. So this was the relation that we had used when we solved this question, right? No reflected wave, so we considered Z not equal to Zn, right? So this is the relation, okay? Now, when ZL is equal to 0, that is when it's a short circuit, okay? So there you will have the reflection coefficient as -1. That means there is a phase that would come in. Okay. So here phase would be pi because it's forward and now it's a backward moving wave. So it's a with the same amplitude, it comes out to be pi. So now if you solve it further, let's simplify it, you would see that you would get an expression like this. So this is now a standing wave. When you have terms like sine Bz into sine omega t, it's a standing wave. When you have sine Bz, some beta z minus omega t, that's a propagating wave. Okay. But this is now a standing wave. So similarly, if you have ZL is equal to infinity, you would again get a standing wave. Okay. So there's a relation which relates the, reflection coefficient to the standing wave ratio. Basically, if your reflection coefficient modulus is 1, that means whatever will go, the same amplitude will come in. So if there will be a standing wave, the maximum amplitude will be 2 into V naught plus and the minimum will be 0. but that is not necessarily always true. If your reflection coefficient modulus is less than 1, that means the maxima of your standing wave will be smaller than 2V0, and your minima will be larger than 0. Okay, so how much larger, how much smaller, that is given by the standing wave ratio, which is given as related to the reflection coefficient by this relation here. So in a question, if you know Z0 and ZL, you can use it to find your reflection coefficient. Once you know the reflection coefficient, you can use this relation to find the standing wave ratio. Okay, so given reflection coefficient, one can find S and vice versa. So yeah, I think this is it. Thank you. You guys have any question?
Ma'am, in a previous problem, I have a doubt.
Yeah.
So V in at ZL.
Yes.
So, ma'am, can you go to the slide? V in at is it equal to minus?
I'm not able to hear you properly.
So
V,
here, no. Next slide.
this one?
So here, find VL in V means. So here the line is a lossless. Even though it is a lossless, so here there is a phase shift will be occur. No, correct. If a length get increased, there may be a phase shift will be occur. So we will not supposed to get a same phase 30° at that VL equal to at Z equal to at that load side, correct?
Okay. What you mean is
Here-
why we are getting this, like why it is 30 here and the same 30 here? Something like that?
Right.
That's the question?
Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am. Because here we added as some length. If we added a length means the phase may be varied at a
Okay.
load side. So the options may be 2.5
okay,
e power
okay.
minus J60. Correct? Or we
Okay,
have to follow e power
understood the question. Yeah. Okay, let me think. So first is that because it's lossless, that means your alpha is 0. Okay.
Ah.
So now the question is, why does the phase remain the same? Right? Okay, 1 second. So you start with this part. We know V. 1 second. No. 1 second. That's not the. No. So we are not taking into account. There will be a phase that would come
phase
in
variations, correct.
when there will be a transmission from here to here, right? But we
Yes,
are
ma'am.
taking into now. See, we know VS at this part. Okay.
Yes, ma'am.
We know VS is this. We know there is a potential drop here and there is a potential drop here. We are not here. We are not taking into consideration the transmission along the transmission line, right? We start with some potential and there will be a drop here and here. So in this part, what I meant is in this part, there is no reason for a new phase to come in, right? So if you start with 10 e to the power J30, no phase lag should come in because of the potential, because of this part, right? So the same thing flows here. Now this is the potential at the incidence. From here, when it transmits through the transmission line to this part, obviously there will be a phase difference. So when you find VL, obviously new phases will come in.
I mean, that's why I'm saying the right answer may be minus 90, maybe. Because
Minus
the
90.
voltage e power minus J60, sorry, 2.5. So initially it is 10 volt, and after that phase of V in the voltage get dropped to 5. After in that place of VL, it may be again dropped to 2.5 or again 5.
Okay, so
The potential drop will be there or not, ma'am? Because it is a discharged lossless line.
Yeah. Let me tell you again. What you are considering is what is the new phase that is coming in due to transmission along this line, right?
Yes, ma'am.
Yeah, but what the question is asking is, so suppose this part of the question is basically nothing but, so what it is telling you is that you have some incident voltage, okay, and there is a resistor here, okay, and there is a net resistor here. So here you know it is 10, okay, and some e to the power j30. Now there is no reason for the phase to change while it travels this resistance, right? So that means
Okay.
at the incidence, see here we are talking about V in. We have still not
Okay.
transmitted through the wire. Okay, so it's Vs, there will be some drop here and there will be some incident drop here. Obviously,
Okay.
once it transmits through the wire, there will be an additional drop. That's why your VL will change, right? This, the, the phase that would come in because of the transmission will change the potential phase at VL, not at V in. Okay, at V in, it is Vs,
Okay.
which is transmitting. Okay, if there was some transmission line which would result in a drop at this point, then obviously this would have a new phase. That is not the case, right? So here, if you
But
start,
what about
yeah, tell me.
what about the voltage? Voltage will be the same 5 volt.
Yeah, so
80.
now consider the case. So two things is there. First is phase and another is amplitude, right? So first is you first understood that at V in there should not be any new phase that would come in, right? Because it is traveling from here to here. So first there should not be any drop, any new phase coming in because of this part, right? So if this is 10 EJ30, there should also be something into EJ30, right? That is what is being propagated till here. So your V in should have a phase of e to the power j30. Now the question is, what is the amplitude? So because you have an extra resistance here, there would be a drop here. Now, how much drop? That depends on what is the ratio of your resistances. So from the first part of the question, if you now get that this is 100, okay, and this is also 100, right? So then there should be an equal drop. So that means now your amplitude drops to 5.
Okay.
The phase that you are talking about would come into picture when you take into account the transmission through this line, right? At Z in, we have not transmitted yet. We are just considering what is there at the incidence.
Okay. Okay. The correct options may be a D. Correct.
The correct answer should be 5EJ30. Because this
Find
should,
VL in B.
acha,
Find
VL.
VL in
Acha,
B.
VL.
That correct answer is a 5E J minus J60. There is a only variation in phase, not a voltage drop. Correct.
No. 1 second. So when for VL, we have to follow this process, right? Because now you have to take into account the effects because of your transmission line. So there, if you use this relation, so you can see that this is the V naught plus, okay? And there it's 5V minus plus this terms that come in, right?
Okay.
Because your load is not matching with Z naught. So there is there are these effects that would come in. So not necessary that at VL, it should be 5.
Okay, ma'am. So we have to use a formula to find out what is that VL.
Yes. So here what would happen is you would see that you would have some additional phase coming in because of e to the power j30 and this term j90 minus e to the power minus j30. This will also be a j here. Sorry. So you have to solve this to find the argument like this phase. And because you have this term, you have this 1 plus TL term. So your amplitude will also change. And you have to
Okay.
solve it to see how much. Okay.
But according to that concept, if it is a distortionless lossless line means we have to get a same voltage, but because of the load impedance at that mismatching, there may be a voltage drop. Correct. Load impedance may not be equal
So,
to that input impedance.
yes, exactly.
Okay.
Yeah.
But what I thought that so it is a lossless line, so maybe the phase variation. So the options may be D 5e power minus j60.
So for lossless,
But
yeah. Tell
but
me.
according to your concept, the answer may be 2.5 e power minus j60.
Yeah, yes. So because you have to solve it because see, the only condition that comes in because of the lossless cases in gamma, you can put alpha equal to 0, right?
Yes,
Lossless means the like only this part you can consider that the wave that is coming in will not have a exponentially decaying turn. That part will not be there, right? But there
Okay.
there will be some reflection from this part, right? So that also has to be considered.
Okay, ma'am. Thank you, ma'am.
Yeah, yeah.
Understood.
Okay, any question from anyone? Okay, so if not, let's call it a day. Thank you.
Thank you.
Thank you.